Let me begin by, again, I'm collectively thanking Andreas for all the efforts he's putting into this and his team of organizing committee members. And you have to go in the back to sort things out, I understand. So as you see from the title, we will be talking about a theme by Harvey Friedman and the variations on this theme. So the natural question is, what is this theme? The actual statement is every non-standard model of ZF, Zermelo-Frankel set theory, or piano arithmetic, that is non-standard. So non-standard is very important, is isomorphic to a proper initial segment of itself. So let me elaborate on this a bit. A non-standard model of piano arithmetic is familiar to everyone in the audience. It's basically a model of piano arithmetic with an infinite integer. A non-standard model of ZF, the picture is more complicated exactly what that is. Well, it's a model with a property that there's an infinite descending epsilon chain. So we could find a sub 0, a sub 1, a sub 2, etc. that form an epsilon descending chain. So the model of ZF that is non-standard need not have non-standard integers. The non-standard feature of it could be showing further up. Initial segment for the, yes. Oh, yes. Countability is absolutely necessary here. I go back to your comment about countable model theory is what counts. You're right. Everything that comes here would be about countable models, and there are easy counterexamples to this statement. Yes, that I wrote down. If you take an omega 1 like model of ZF or PA. Yes. That's right. Every countable non-standard model. I'm amused by the fact that the story I'm about to tell was sometime around 71, plus or minus 1. Jim Schmelb was at Yale at that time, and Yoram Hirschfeld was finishing his thesis. So the person who was watching TV instead of working on his mathematics was Hirschfeld. Okay. Harvey talked about his recent work when he was asked about what have you done recently. And you see the theorem that I began with, the correct formulation, is actually part of a package of results about embeddings between models of arithmetic and set theory. And in a way, it's the crowning feature of maybe these theorems. And that's what he was talking about actually in this show. And that's exactly what Hirschfeld needed for a critical argument in his thesis. And in case you're curious, what was the statement? He showed that every countable model of PA can be embedded in a non-trivial homomorphic image of the semi-ring of recursive functions, just in case you were curious exactly what this result was. Okay, so the rest of the talk, I will go back and give you a context for Friedman's theorem in terms of what happened slightly before Friedman's theorem appeared and what happened subsequent to that up to about 1997. I give you some sort of synoptic history of how this result was rather refined and extended, hence the idea of variations on the theme. And then at the very end, I'll just show you some very quick examples of some very recent work that is not yet published yet by 4 different people. Before getting there, let's just also make sure that we all know where this result comes from. It comes from a paper of Harvey that appeared in this proceedings of a meeting in Cambridge. Harvey has another paper in the same proceedings, and I'm wondering if this other paper, which I know is on intuitionistic logic, involves the A translation. I'm not sure.
No, I think that's a cleaning volume. The A translation. This is Cleaning's notion of realizability.
There we go.
This
okay.
is all realizability. There's a separate paper, I believe, in a yellow book, in the yellow series.
Yes.
I think it's Cleaning's Symposium.
Yes, that's also yellow, yeah. So that's a few years later, yeah.
It was very moving. When I gave this A translation, and I actually gave the derivation, and right in the middle when it came down to, the trivially verified one, Blackboard, I got a person with one. It was very moving.
Now, Harvey's result about self-embeddings that I'm talking about is actually a really minute fragment of this paper, and I just wanted to show you just the contents of this paper. As you see, it's not a short paper, from 539 to 573. Introduction of a few pages. It's a very nice introduction. Preliminaries, definitions, key theorems. And then section 2 talks about standard systems in a very general context. Most of us know standard systems in the context of models of just non-standard arithmetic, but exactly, this was anticipated by Scott, but you took it and extended it beyond just the arithmetical setting. And then in section 3, Harvey computes the order type of ordinals in non-standard models of set theory. As you see, there's a reference to admissible sets, so Harvey's not just looking at ZF, but much weaker fragments. It's in section 4 that is highlighted, that, as you see, is also 3 pages, that you have the self-embedding results. So everything is in these 3 pages. So I'm, in a way, talking about a minute fragment of just one of these sections. Section 5 is about submodels of full second-order arithmetic, and then section 6 goes back to set theory. Just for your maybe information, the last page, which is reference and errata, there are 3 references: the Dana Scott paper, a Barwise paper, and McDowell-Specker. Very, very frugal. Okay, so here is the synoptic history. There was a result actually which was published in '62 before Harvey's result appeared, which is a precursor of Harvey's result, and this has a very distinguished pedigree because it's a question that Dana Scott asked, whether it's possible for a non-standard model of true arithmetic, meaning theory of natural numbers, to be isomorphic to a proper initial segment. And Vaught answered that in the positive. It eventually was published in the '62 paper with Morley, and the example he used was saturated or special models. These are rather large models; they're never countable. And '73, the pivotal paper appeared with the result that I just mentioned, and now we see the avalanche of results that come after that. But the avalanche is slow. It's fast here in this short talk, but at any given time, you would think the subject is complete. Okay. So the next result that I was able to find out, I've been working on this topic for the past 2 years or so, was a dissertation of Alex Wilkie, and he had various extensions of Harvey's result, and one of the variations was that this copy of the whole model that is isomorphic but an initial segment, they're quite abundant. There are continuum many such copies that you could find. So there's an interesting new argument you need for that. And then Hamid Lesan, in also a dissertation, and by the way, another Iranian, he was a student of Wilmer's at Manchester. And he was able to show that you don't need full PA for the Friedman result. It's sufficient to have the pi2 consequences of PA. Okay. As long as the model is one tall and one extendable. So the result looks technical, but the definitions are quite natural. One tall means the set of sigma 1 definable elements are not cofinal in the ambient model, and one extendable means there's an end extension, M star, of the ambient model, which satisfies I-ditto 0 and has the same sigma 1 theory. Now, the Lesan result was substantially fine-tuned, as we'll find out. But before we get there, again, we have to thank Smorinsky, whose name has come up already in Albert's talk. He gave influential lectures and very, very nice papers that he wrote that he systematized how to prove Friedman-style theorems revolving around one key notion of partial recursive saturation. So this notion of recursive saturation back in the early 70s when Harvey was writing his paper was not as well known as it is now. And in a way, the bringing the result to the masses was done by Smorinsky. So some standard model theoretic tool can be applied to get these results. Okay, so before I talk about what you're seeing on the screen here, let me just first point out that in the Friedman theorem, when you're beginning with a non-standard model of PA and you're trying to find an isomorphic copy of it as an initial segment, the argument itself very easily shows that this copy can be found arbitrarily high in the model. You don't have to work extra for that. But the question came up, can you find it arbitrarily low? So this apparently was considered by a number of people, and in particular Stanley Tannenbaum, who had looked at the proof and he thought he has some sort of idea, but he'd never carried it out, suggested to Leonard Lipschitz that such a result could be true. That if your model is Diophantine correct, that it doesn't solve any Diophantine equations that was not already solvable in the standard model, then you could push this isomorphic copy arbitrarily low in the model. So this was a paper by Lipschitz. And then this next one is extremely esoteric the way it's written. Jeff Paris noted that an unpublished construction of Robert Solovay shows that every countable recursively saturated model of now I delta 0 plus b sigma 1, so much weaker than I sigma 1, is isomorphic to a proper initial segment. So this paper of Jeff has appeared, but the paper of Robert Solovay, even upon email contact with him, he was not able to put his hands on the paper, so it seems to be lost forever. But at least the result was transformed and preserved by in the Jeff Paris paper. So this result is very nice. Yeah.
So he reproved what Solovay did publish.
Exactly, yeah. So in the previous result that I was just showing you, I delta 0 plus b sigma 1 was at work, but the model was not just non-standard, but more non-standard and recursively saturated. If you lift the recursive saturation, which is of course absent in also Friedman's theorem, you might wonder how much arithmetic is needed for the Friedman results. So this was a question that occupied people's minds since Leson's thesis. So that was a few years before, as you see from here, is 85 now, that Kostas Dimitrakopoulos, another student in Manchester, he managed to get the argument to work for b sigma 2 added to I delta 0. And it's a very beautiful argument. It's the kind of argument you can nicely discuss over coffee, give a napkin proof of it. But this is not the last word. The last word came 2 years later by Jean-Pierre Rosser in France. As you see, it's a very international set of people we're looking at, jumping countries and continents. So he managed to prove the result for I sigma 1. Moreover, he gave the following fine-tuning, that if you put your finger on a member of the model that you're looking at, the non-standard model, and you want to have an embedding from the big model so that in your embedding, not only this element you put your finger on, but every element below it are fixed. So the embedding goes from the big model to an initial segment, but pointwise fixes the initial segment determined by this element A. Then still the theorem goes through, and indeed, and this is also what's wonderful, there's a reversal. If you assume this property, you can buy I sigma 1. So this was the first, in a way, geometric characterization of I sigma 1 in terms of how you can move the model around. Now, the half of the result that has to do with I sigma 1 was rediscovered with a different argument by Dimitrakopoulos and Paris, where the argument is actually quite different, had the same result, and they also fine-tuned the Leson result that I had earlier. In the Leson result, we have pi 2 pa, this is the line before last, but in their version, we have a very weak fragment, I delta 0 plus x plus b sigma 1, EFA, that was also discussed earlier. And now we come to exposition again, and also you get to see a very precise statement of like the textbook version of Harvey's theorem, which we owe to the efforts of Richard Kay when he wrote his book on models of arithmetic in 1991. I hope so. Yes, there it is. Suppose we have so this version has actually a target. You have a model M, and you have an A and a B in the model, and you want the initial segment to lie strictly between them. So it turns out this is the right way of actually going about proving the result, because by just specifying these two parameters, somehow a natural flow will occur in the proof. So the following two statements are equivalent. The first statement is written down here, but if I were to say this in a more intuitive way, you could think of it this way. If you apply a partial recursive function of m to A, you will land below B. So A and B are so far apart that any existential claim made with parameter A is witnessed already before B. Okay. It's important here that we have partial recursive functions because there's another result we're going to be seeing which talks about total recursive functions. So this version is exactly as you see, talks about A and B being far apart from the point of view of partial recursive functions of M. Oh, the delta is a typo. It used to be a delta all across. Thank you. So everything should be a sigma. So that delta is a sigma. Yeah, I should fix that. Yeah. So now we have two typos. Okay. At least. Okay. Thank you. Yeah, the delta in the very last should be a sigma. Yeah. I had a delta zero formula called delta, and I changed to sigma zero. Yeah. Actually, in this formulation, there are two typos. Let me just come over here. So that, okay. The sigma zero is okay the way it stands right now, but if you read it as sigma n, the result is going to be much better understood. Okay. So again, that sigma zero in item number 1 should be sigma n. Okay. For number 2 to go through, because in number 2, basically, you not only want to embed between A and B, but you want that initial segment to be sigma n elementary. If you just want an initial segment, that would be sigma 0 elementary. So here you have basically the parameter n, if number 1 also had sigma n written down there. In general, you cannot have full elementarity of the initial segment, but as you see, we can always arrange partial elementarity for any specified n. Okay, so in a way, in some sort of way, the penultimate result in this direction has been proved by Kazuyuki Tanaka in Japan, where he has proved this result for WKL0. And I'm sure you would wonder, if you haven't seen this result, why was Tanaka trying to prove this result? Because Tanaka's work was not exactly in self-embeddings. You see, he was doing reverse mathematics, and he was trying to formalize some non-standard arguments that would only go through if you had WKL0. And one of these arguments was the construction of the Haar measure. All the known proofs up before Tanaka's paper appeared with Yamazaki, ACA 0 was what was needed for getting Haar measures to be constructed. So the significance of this result in Tanaka's paper is precisely that with this result, you can implement a non-standard proof of the existence of Haar measures in WKL0. The reversal is easy. You could show if there are Haar measures, then you get WKL0. So it goes back to, again, Sam Sanders' list, one more item in that list. Okay. So in this case, we have a two-sorted structure, as you see, a model of WKL0, and the embedding has to send also the classes in the right way to their initial segments, as indicated in the bottom of the chart. I've recently written a paper that has been accepted for publication that has a new proof of Tanaka's theorem. Okay, now I have just basically 4 slides, each one giving you just a taste of the results that have appeared recently that, as I mentioned, have not been published yet. The first one is one that I'd like to begin by specifying the definition of a total M recursive function that I alluded to earlier. So when you specify a model of arithmetic and you talk about its recursive functions, you're talking about exactly functions that are definable with the parameter-free sigma 1 formula. Okay. So with this definition in place, then this is the result due to Shavrukov, who also needed it for his purposes in giving some analysis of dynamic properties of RE sets, interestingly. This was a paper that was presented in the Logic Colloquium last year and will be appearing. But basically, this is exactly the analog of what you saw earlier, except we're looking at partial. Instead of partial, we're looking at total. Now, let me just jog your memory a bit. In the previous slide, the embedding fixed A. So this target is from A to B is a target, and you're trying to fit the model between A and B. if A and B are so far apart that every partial recursive function applied to A lands below B, then not only is there an embedding between A and B, but that embedding fixes A. But very often, you might not be interested in fixing A, just want a model between A and B that is isomorphic, and that's exactly where you get this version of the story. The next one is due to Till-Lock Wang, who's also known informally as Lawrence Wang, who was here for some time, as a postdoc. So he looked at basically the Solovay proof, the one that was rewritten by Paris, and he saw that he could push it through to actually give a characterization of WKL star 0. He also used some work of, I should say, Rosaire. Okay. So I'll mention exactly what is RCA star 0. But the characterization, as you see, has to do with self-embeddings. So it's very much Tanaka-like, but it's giving you 1 and 2 being equivalent. And RCA 0 is defined in the bottom part of the slide. And a good equation to have in mind is it bears a relationship to exponential function arithmetic in B sigma 1 that WKL 0 to I sigma 1. So this result is useful for implementing various non-standard constructions in even weaker systems. Keita Yokoyama's name also has come up earlier. So he gave a characterization of pi-1-1 comprehension in terms of self-embeddings in a paper that will be appearing, which has to do with the image being a Ramsey cut, a strong Ramsey cut in the model, which you were seeing in blue in the bottom. And the very last result that I'm mentioning, which is the next slide, has to do with fixed points. It's a result of mine. But before I put the rest of it on the board, let me just point out, if you look at the Friedman result and you're wondering how much control do I have on fixing elements? Well, at some point I mentioned the Rosaire result, which says if you put your finger on an element, you can fix it and all of its predecessors. But in general, if you ask yourself, what has to be fixed for sure? Well, the sigma 1 definable elements have to be fixed. Okay? And Zhako Mihailovich, already about 15 years ago, proved that if something is not sigma 1 definable, you can move it. Okay, so for anything that is not sigma 1 definable, you could move it. Now, one can ask, what if you want to move all sigma 1 undefinable elements in one fell swoop? Okay. And that's what this next result basically answers. If you, so as you see, countability is present here. Countable non-standard model. You can arrange for the fixed point set to be the set of sigma 1 definable elements. That's the K1 of M is exactly the set of sigma 1 definable elements. It's a terminology from models of arithmetic. Exactly when the set of natural numbers forms a strong cut in the whole model, which means if you adjoin the standard system to the standard cut, it's a model of ACA 0. That's another formulation of what it means to be a strong cut. That concludes my survey of recent results and my talk. So let me thank Harvey for giving us a beautiful theme, and congratulations for his award. And now I can give my place to the next speaker.